In grade 1, you learned to add scalars. Your grade 1 teacher probably didn't call it adding scalars, but in the end, that's what you were doing. 1 plus 2 was equal to 3. 3 plus 4 was equal to 7. Always. There were no exceptions to that. It had to be. If you said 3 plus 4 was equal to 6, you were wrong in grade 1. Then when you went to grade 5, grade 6, you learned to add 3 plus 4 a little bit differently sometimes. Maybe the 3 was a negative value, and the 4 was a negative value. In that case, 3 plus 4 could be equal to 7, or it could be equal to 1, or it could be equal to minus 1, depending upon the signs of the 3 or 4. In grade 5 or grade 6, when you learned to do that, you were really adding vectors together, although it was vectors in one dimension, north and south, or east and west. Today, what we're going to learn to do is add vectors in 2 dimensions, where 3 plus 4 does not necessarily equal 7, like adding scalars in grade 1. 3 plus 4 does not necessarily equal 1 or minus 1, like adding vectors together in grade 6, but rather maybe 3 plus 4 could be equal to 5, or conceivably even some other number. When we're adding vectors together in 2 dimensions, like not 3 plus 4 is 7, not 3 east plus 4 west is negative 1 or 1 west, but rather 3 north and 4 to the east is what? Well, the goal when we're adding those vectors together is this. This is important. Remember this goal, because we always want to meet this goal. The goal is to get what we call a vector diagram that is a right-angled triangle. What does that mean, a right-angled triangle?
It's a triangle, one of the angles is 90 degrees.
Good. A triangle where one of the angles is 90 degrees. Okay, that's a right-angled triangle. The goal is to always get a right-angled triangle that is a vector diagram. And I'll show you in a second how to draw that vector diagram and get that vector diagram right-angled triangle in order to complete the sum of these vectors. And then, of course, we've got to use a little bit of trigonometry. Sine, cos, tan. You guys remember that trig? Sine, cos, and tan?
Yes.
SOHCAHTOA? Yeah? Here's the rules of drawing your vector diagram. You need to draw each vector as a line segment with an arrow showing the direction. So for instance, if I'm trying to add 3 meters to the east, then I'm going to draw a vector that's a line segment with an arrow pointing to the east. 3 meters to the east. If I want to draw a vector that is 4 meters to the north, then I would draw a line segment that's slightly longer than the 3, because it's 4. Right? The length of it is roughly proportional to the magnitude. I draw it this way, 4.0 meters to the north. If I had 7 meters to the south, then it would look something like this. Bottom line is, I have to draw each vector that I'm trying to add together as a line segment, and then an arrow on the end of the line segment showing the direction. Don't forget the arrow. Don't ever draw a vector diagram, well, don't ever draw it like this. We want a right-angled triangle, but we want arrows on those line segments. Now remember, you should always draw your vectors head to tail or front to back. What does that mean? Well, if I'm adding 3 plus 4, let's say I'm adding these 2 vectors that I have up on the board right now, 3 to the east, 4 to the north, then I've got to draw it like this. 3 east, the arrow is the head of a vector. Draw it to the tail of the next vector. The back of it is the tail. So it's drawn head to tail, or the front of one vector to the back of the next vector. Does that make sense? You can't draw it like this. Don't draw it like this. What's wrong with that? That's drawn head to head. We don't want it drawn head to head. We want it drawn head to tail. Now, there is one more option. Okay, this is head to tail, but so is this. Isn't it? Isn't that drawn head to tail, front to back? Absolutely. Both of those are correct. Okay, both of those are correct. Doesn't matter which one you draw first. If I was adding scalars together, we'd say 3 plus 4 was equal to 7. But we could also say 4 plus 3 was equal to 7. Doesn't matter which order you add them in, right? Adding vectors is different, but the order is still irrelevant, just like it was with adding scalars together. Now we've got to combine them. Now we've got to actually figure out what the sum of these vectors is. The sum of these two numbers, 3 and 4, whatever the numbers are, is. To do that, we have to draw what we call the resultant vector. And I'll either usually draw that in a different color, or I'll draw it as a dotted line. It doesn't really matter, a different color or a dotted line. Sometimes I'll do it as both. The resultant vector should be drawn from start to finish. This is the start of my vector diagram. This is the finish of my vector diagram. I'm going to draw it from start to finish with an arrow pointing toward the finish. This resultant vector that I'm going to label R, that is the sum of the vectors. 3 plus 4 is equal to R. Now I just have to figure out what R is. How am I going to do that? I can figure what R is by, Jacob? Well, I could use, well, I wouldn't need to know the angle. I could find the angle, this angle drawn at the start of my diagram by using trigonometry. And I could find R by using a squared plus b squared equals c squared. In other words, the Pythagorean theorem. Is that okay? So in this case, 3 plus 4 is equal to R, and because R is a vector, we need the angle there. All right, let's add a few vectors together. These are all vectors because they all have direction, but you're going to see that some of them are vectors in one dimension. We're going to use the old grade 6 rules of adding to add those vectors in one dimension. But when we come across the ones that are in 2 dimensions, then we're going to have to use, well, now the grade 11 rules of vector addition here. We're going to say for the first one, 10 meters north plus 20 meters to the north. We don't need to draw that, although we could. 10 meters to the north plus 20 meters to the north would be what? 30 meters to the north. It's not necessary to draw the vector diagram there because, well, clearly you can do it without the diagram. Next one, 10 meters north and 20 meters south. Again, you could draw the vector diagram if you wanted. It's not really necessary. 10 meters to the north plus negative 20 meters or 20 meters to the south gives me negative 10 meters. Or what else could you say? 10 meters to the south. So no crazy vector analysis there, no crazy resultant vector, no crazy triangle or dotted line or anything like that. All we do is do the grade 6 rules of vector addition. What about this one? 10 meters north and 20 meters to the east. This is 2 dimensions, north and east. Right? So this is where we want to draw that vector diagram. I've got 10 meters to the north, and I've got 20 meters to the east. Is that drawn okay? Is that drawn okay? I'm not quite finished yet because I haven't drawn the resultant, right? But so far, is it good? Yeah, it's drawn head to tail, right? Arrow to back, front to back, head to tail. That's okay. We're going to solve for R, the resultant vector, which is drawn from start to finish, from where I began to where I finished. We're going to solve for R by using the Pythagorean theorem, a squared plus b squared is equal to c squared. If a squared plus b squared is equal to c squared, then c is the square root of a squared plus b squared, right? So we're going to say R, which is the value of c, is the square root of 10 squared plus 20 squared. So it's the square root of 500. We get 22.36, which by rights we should round that to 22 meters. There we go. 10 plus 20 is equal to, well, according to these rules of vector addition, 22. But we also do need an angle. We'll worry about that angle later on. We won't sweat that right now. 10 meters west and 20 meters south. We've got 10 meters to the west We've got 20 meters to the south right here. Is that drawn okay? Head to tail, front to back, that's good. My resultant vector is drawn like this, from start to finish. There's r, there's theta. R is a squared plus b squared is equal to c squared, or r is equal to the square root of 20 squared plus 10 squared. And it works out to be 22 meters. You get the same answer for the last one as you do the third one here? Yeah, for the magnitude you do. What would be different about this if we continued on and completely solved this question? The direction is different, right? Direction is important, but we'll deal with that once we've kind of got the hang of finding the magnitude of it. All right, let's take a look at the first three questions that I gave you on that worksheet. Look at the first one. We're adding 20 plus 10, 20 to the east plus 10 to the north. Is that drawn okay so far? Yeah, it's drawn head to tail, right? You can see the head of the vector to the tail of the next vector. So is this one, head to tail, and so is this one, head to tail. They're all drawn correctly. Now the resultant vector, that's that dotted line vector or different color vector, is always drawn from start to finish. So I'm going to draw that one here like this, from start to finish, from here to here, from start to finish, and from here to here, from start to finish. Is that okay? Now, let's find the value of r. 10 plus 20 is equal to what? 15 plus 10 is equal to what? 10 plus 5 is equal to what? We're going to find the value of r in all three cases by doing the Pythagorean theorem. R is equal to the square root of a squared plus b squared. Remember, r is like c in math class, right? A squared plus b squared equals c squared, or c is the square root of a squared plus b squared. Okay, r is the longest side of my triangle, and it's always going to be the square root of a squared plus b squared. What do I get there? R is equal to the square root of 500, 22.3, I think it is, right? Pretty much the same question as we had as our example. Now let's take a look at the next one. We're going to say in this case r is equal to what? 15 squared plus 10 squared. Let's square root that. 225, 325, square root of 325 is what? What'd you get? 18? And for this one, we're going to say r is equal to the square root of 10 squared plus 5 squared. By the way, does it matter which order we put those numbers in? 10 squared plus 5 squared or 5 squared plus 10 squared? Not at all. Not at all. Let's do this one on the calculator just to make sure that you guys are okay with this. Do what's inside the square root sign first. Okay, just like I say, do what's on the bottom first, do what's inside the square root sign first. Let's say 10 squared plus 5 squared equals. And then let's square root that. We end up getting 11.18 or 11.2. There we go. Make sense? Now, strictly speaking, we do need to solve for an angle because it's a vector. The angle is always drawn at the start of the diagram. So we'd solve for theta there, we'd solve for theta there, and we'd solve for theta there. But we'll worry about that later on. Okay? So far, so good? Okay, what are we going to do if we're adding more than one vector together? Or, sorry, more than two vectors together? Well, we have to use what we call vector components then. All right. So what do we mean here? Add the following vectors together, three vectors, use components. If I said 25 meters to the north and 20 meters to the east, easy. Well, not easy, but we'd draw it just like we drew it before, front to back or head to tail, draw a resultant vector from start to finish. But if we draw this one, 25 meters to the north, watch this, 25 meters to the north, 20 meters to the east, and then 30 meters to the north, I could draw a resultant vector from start to finish, but that's not a triangle. There's no easy way to find the value of r there, right? Don't break that up into two triangles or whatever. Do this. Break it up into components, x and y components. Right, Mackenzie? What do we mean by that? Well, this is x. East-west is x. And north-south is y. So if I'm saying 25 meters to the north for the first one, 20 meters to the east, and 30 meters to the north, how much of that first vector, 25 meters, is x? Remember x, east, west. How much of it's x? How much of this 25 is across? None. So we're going to say the x component of that first one is 0, and 25 of it is up. 25 of it is north-south. Agree? Does that make sense? How much of that 20 meters is east-west? 20 meters. How much of it's north-south? 0, because it's all east-west, right? How much of this is taking us up? None. How much of this is on the x-axis? How much of that 30 meters is this way? None. How much of it's up, down? 30 meters. Now let's add these up. 0 plus 20 plus 0 is 20. 25 plus 0 plus 30 is 55. Now let's redraw this. 20 this way, 55 this way, right? Head to tail. And my resultant vector is, hey, look, it's the same resultant vector, right? Except that this time it's in a triangle. So this time I can do the old Pythagorean theorem here. R is equal to 20 squared plus 55 squared, square root that on our calculator just to make sure you can do it. Inside the brackets first, square root that. .5 or 59 meters. And we'll worry about finding the angle later on. What's the same about this question versus the questions you were working on a few minutes ago? This. But in this question, you had to get there. You didn't have a triangle. What's the goal? Remember I said don't forget the goal. Get a right angle triangle. We didn't have a right angle triangle here, so what are we trying to do? Get a right angle triangle. We did that by taking the x and the y components of each vector, adding them together, combining them, and turning it into a right angle triangle. Yeah, question?
Could you divide the first one into two triangles and do it that way?
Technically, you could divide the first one into two triangles, but that would not be the way to go. That'd be pretty challenging actually to end up doing that. Like to solve for this, and then to solve for this would be really hard because we wouldn't know how much this and this is, right? It's not just 10 and 10. So without knowing exactly where that intersects that line, that's virtually impossible to do. Okay, theoretically correct, but mathematically very, very difficult. Let's do another example here. This time we have 4 vectors this time, right? We have 10 meters to the east. Then we have 15 meters to the south. Notice my 15 meters drawn a little bit longer than my 10 meters. Should be, right? Is that drawn okay, front to back, head to tail? Yeah? Next one, I got 12 meters to the west. That's drawn a little bit longer than the 10, a little bit shorter than the 15. Is that okay? What's wrong with that? Yeah, this is head-to-head, isn't it? That's wrong. All the vectors that I'm adding together must be not head-to-head, head-to-tail. So I don't have to change that much. I just move it over a little bit, right? And then I draw 20 meters to the south. Good? That's correct. Are they all drawn head to tail? Absolutely. Now the resultant vector should be drawn from start to finish, should be drawn from here to here, from start to finish, but that's pretty difficult to find. Okay, somebody suggested in the last question that maybe we break it down into 2 triangles. This one would have to be like, I don't know, a couple triangles and a rectangle. It is not. the way to go. Definitely not the way to go. So what are we going to do? If we have more than two vectors like this, let's break it up into our x's and y's. Okay, vector 1, 2, 3, and 4. How much of vector 1, how much of this 10 meters is x? Remember, x is this way. Good. All of it is x. All of that 10 meters is x. How much of that 10 meters is y-axis? Ethan, how much is y-axis? 0. None. Next vector, second vector, the 15 meters. How much of that 15 meters is x? Take a look over here. You see what's x here, right? How much of that 15 meters is on the x-axis? None. None of it. How much of it's on the y-axis? 15 meters? Negative 15 meters. Why negative, Jacob? Because it's going south. It's going downwards, yeah. Look at the next one, 12 meters. How much of that one, Mackenzie, is on the x-axis? Almost. Negative 12. How much of that 12 meters, Dylan, is on the y-axis? 0. It's all x, right? And then the next one, the final one, 20 meters. How much of that 20 meters is on the x-axis, Sean? None. And how much of that 20 meters is on the y-axis, Rachel? Yep, you. How much of it's on the y-axis? Negative 20 meters. Good. Good. So let's add these up now. 10 plus negative 12 gives me negative 2. Negative 15 plus negative 20 gives me negative 35. So now I'm going to add these up. I'm going to say negative 2 plus negative 35. By the way, I don't need to label that as negative because the direction of the arrow shows me that it's negative. The resultant vector is drawn from start to finish. Look at that resultant vector. Look at it. Doesn't it look just like the resultant vector that I drew in the first diagram? Absolutely, it should. It's the same vector. But now, remember what the goal was? What's the goal? Tim, what was the goal?
To find odds.
Yeah, before we do that, though, how do we get it? What's always the goal? Get a right angle triangle. Good. Get a right angle triangle. Now, we've got this resultant vector in the form of a right angle triangle. We didn't have it in a right angle triangle before, right? It was difficult to find. Now it's easy. Now all we got to do is say r is equal to the square root of 2 squared plus 35 squared, whatever that works out to be. Going to be somewhere around 35 point something, 35.1. And, of course, we could find the angle here as well, drawn at the start of my vector diagram, but we're not worried about that quite yet. So what's similar about this? What's the same about this with the questions that you were working on in worksheet just a few minutes ago? This. You got a right angle triangle, do the Pythagorean theorem. What's different about it? You had to get a right angle triangle. Keep the goal in your head. Know what the goal is. The goal is always get a right angle triangle. So let's do what we have to do to get there. If you have it already, like you did in the 3 questions you already worked on, that's great. If you don't have it, then get it by doing the x and y components and then redrawing it like we have right here. When you finish writing that, I'll get you to take a look at your worksheet again and take a look at questions 4 and 5 on your worksheet. Again, don't worry about the angle in questions 4 and 5. Just find the magnitude of the resultant vector. In other words, do your x and y components, redraw it as a vector diagram, right angle triangle, and then find the hypotenuse. For questions 4 and 5, because there is more work to it, you're probably going to need to do that on a separate piece of paper. Okay? Bottom line is, wherever you do it, show all of your work, including those x and y components, all of the work that we show on the board here.